speak at the MoCaO lectures and give the, so to say, the last lecture here. So our topic this week was polynomial optimization, and what we have seen so far addressed this equivalence of polynomial optimization and deciding non-negativity of a polynomial. And we saw the sums of squares approach and the SDP approach for that. And today, as the title suggests, we will go beyond that. And yeah, the story wouldn't be complete without a very short introduction. So let me maybe go again over the kind of the motivation. So the key problem is a constraint polynomial optimization problem. So we have a bunch of polynomials, f and g1 to gs. They are multivariate and real. And then our underlying problem is to minimize a polynomial subject to some polynomial inequalities. And we are over the reals all the time. Usually, as you have also seen this week, we write this in a more condensed version like so, where we gather all constraints in such a set K, for instance. This is the basic closed semi-algebraic set defined by these inequalities. And then we want to minimize f subject to x being in this set K. And we usually denote during the talk the optimal value of this guy with fk star. Clearly this is a special case of nonlinear non-convex optimization. And you have seen already by James and Georgina, this problem has countless applications, robotics, control theory, you name it, basically, right? But unfortunately, this problem is very hard, already under very mild assumptions. And that's where somehow this more algebraic point of view comes into play, where we formulate this problem equivalently to deciding non-negativity of a polynomial. So we are equivalently solving this problem of finding the largest real number gamma, such that f minus gamma is non-negative for all x and k. So the real algebraic problem here is deciding non-negativity of a polynomial on either on a set or globally if we are in the unconstrained polynomial optimization case. And this algebraic problem is really a key challenge in real algebraic geometry dating back to the 19th century. You saw results by David Hilbert this week. But in fact, this problem is decidable, but still very hard in general. So the idea that was presented during this week was to find conditions, sufficient conditions that imply non-negativity, but are somewhat easier to check. And that these conditions are really satisfied or useful in practice. They better be satisfied for a significant amount of non-negative polynomials, right? Because you can find sufficient conditions which are easy to check maybe for some polynomials, 1, 2 polynomials, but this is not really useful if this is not valid for a significant amount of polynomials. And these sufficient conditions we call certificates of non-negativity. And during the week, you saw, I would say, the most prominent example of such a non-negativity certificate, namely sums of squares. You learned that sums of squares can be identified via semi-definite programming. But you already heard about the numerical issues here, or the issues of semi-definite programs, right? So, or basically of this general approach with SOS SDP, namely, so first of all, numerical issues can occur. If, for instance, the set given by the constraints has a different or a complicated shape, then numerical issues can occur, but well, that happens, right? But the most crucial issue here is that semi-definite programs are very, very expensive and scalability is a non-trivial challenge. So there are possible improvements to somehow address these issues. So first of all, clearly to create better solvers and find better representations of the problems, right? This is somehow things we always should do when we have applications in mind to just make the computation faster and more stable. Yesterday, you saw an approach where basically the road was taken to relax these SOS certificates even further. You learned about this DSOS and SDSOS certificates, which basically corresponded to cheaper classes of optimization problems, namely linear programs and second-order cone programs. Then also Georgina told you about, clearly we can also exploit the structure of the underlying problem. Like you can think about symmetry or sparsity. But there's also another approach that was not discussed until now, namely finding just new ways to certify non-negativity independent of this SOS SDP approach. And this is exactly the topic of the talk today. To get us all on the same page, I will basically use the same notation as James and Georgina, but in case you forgot, so I will use R sub n to d as the vector space of real polynomials in n variables of degree at most 2d. So usually when we work with these creatures, we want to have a finite real vector space, right? That's this Rx sub n to d. And in this vector space, there live two cones up to now, namely the cone of non-negative polynomials, which we denote by Pn to d. This is the cone which is generated, so to say, by the non-negative polynomials. And inside of this cone, there lives the cone of sums of squares. So the more maybe geometrical picture you should have in mind looks like so. So here, this turquoise cone is the cone of non-negative polynomials. In this cone, there lives the cone of sums of squares. Here, you heard about the result by David Hilbert that somehow said it or gave us a reasoning why we draw this picture like so. Namely, there are clearly non-negative polynomials which are not sums of squares, so it makes sense to somehow draw this cone a little bit smaller. And yesterday you learned about these as DSOS polynomials, and DSOS polynomials, they clearly also live inside of this SOS cone. So from the geometrical point of view, what we are interested in finding another cone inside of this Pn2D cone, which hopefully does not lie inside of this cone of sums of squares. So the outline for the talk is that I will first present this new non-negativity certificate, which is called sums of non-negative circuit polynomials, or SONC for short. Then I will tell you a little bit about the geometry of the SONC cone, and here I want to specifically highlight two properties which stand in strong contrast to the geometry of the SOS cone. Then I will apply really these SONC polynomials in polynomial optimization, what really was our goal, right? And then I show you that this concept of SONC polynomials even extends to something that we call signomial optimization. And in the end, I hope time allows that I will discuss application, namely application in for a chemical reactor system. All right, so let's get started. To introduce this new non-negativity certificate, I really start with explaining what a circuit polynomial is, because this is somehow the building block of this new non-negativity certificate. So a circuit polynomial is a polynomial that has a specific shape. It looks like so. It is very sparse in the sense that it has only n+2 terms. And we somehow separate the last term. So here are n+1 terms. Here is the n+2 term. And this polynomial satisfies certain conditions. that I will explain by means of this picture. So here is the support of a circuit polynomial plotted. So the support of a polynomial, remember, is are the exponents of a polynomial, and I can draw these exponents in a coordinate system as just like points, right, in this coordinate system. And so the conditions that a circuit polynomial has to satisfy are the following. So firstly, the Newton polytope of such a polynomial, which is just the convex hull of the support, so the convex hull of these alpha j and this beta. This is supposed to form a simplex. In 2 dimensions, this is clearly a triangle. So this is the Newton polytope, and you see it forms a triangle. Secondly, there is one specific exponent, so one support point, let's call it beta, that lives in the strict interior of this simplex. And geometrically, I can express this beta, this interior point, then as a convex combination. And this is exactly what is written here. Namely, I can express it as a convex combination of the vertices. Right? So beta is this convex combination of the vertices, this alpha j, and this lambda j for a convex combination have to be strictly positive, sum up to 1. And usually these lambda j are called barycentric coordinates of this interior point relative to the vertices. Okay, so we have a simplex, one strict interior point in the simplex. And then the third condition, this is not really special to circuit polynomials. This is just a condition that any polynomial that wants to be non-negative has to satisfy, namely that the coefficients that correspond to the vertices here, so these alpha j, they have to be strictly positive, and the vertices themselves, so the alpha j, they have to be even, right? So if you think about them as vectors, every entry has to be even. So in short, a circuit polynomial is a polynomial that has a specific structure in terms of this Newton polytope. The Newton polytope forms a simplex with one additional interior point. A circuit polynomial has n plus 2 terms, and you can think about this extra term here as the potential bad term, because if every alpha j is even and the f alpha j are strictly positive, the only thing that can somehow destroy non-negativity of this polynomial would happen here with this term, right? So for instance, if f beta is too negative, or if beta would be odd, then something can happen if you plug in numbers for x. But if I wouldn't have this term, this polynomial would be non-negative always, right? So this is the non-negative, this is the bad term here, this f beta, x beta, and this will define, or this will somehow give me a hint when this polynomial will be non-negative. Let me say maybe one word to the terminology here. So why do we call these polynomials circuit polynomials? And this is because the term circuit, or better, because the support really forms the circuit. So a circuit is a term borrowed from matrix theory, and there, this is just a name for a minimally affine dependent set. So as soon as I remove one element from the set, we have affine independency. But as you see, for instance, this beta you can write as a convex combination, so this is affinely dependent. You already encountered such a creature, namely, in fact, the Motzkin polynomial. This is a circuit polynomial. So the Motzkin polynomial, recall, this was somehow the first polynomial known to be non-negative, but not a sum of squares. And in fact, it is a circuit polynomial. So to somehow show you that this is a circuit polynomial, I have secretly chosen the support of this polynomial really to be this sketch here I draw. So this picture shows you the support of a Motzkin polynomial. So to convince you here, you can think about the corresponding monomial to be x to the 0, y to the 0. So we have the point 0, 0. This would give me the point 4, 2. This is this vertex. 2, 4 is this vertex. And 2, 2 is this interior point. So we have the shape. And we also have this, that the third condition is satisfied, right? So the coefficients of the vertices are 1, 1, 1. So strictly positive. And also the vertices themselves are even. So the Motzkin polynomial is a circuit polynomial. All right, so we have now the circuit polynomial, but somehow we have to connect it with non-negativity. And I claim that non-negativity of these polynomials can be decided very easily, namely with a specific invariant we define with these polynomials, namely the so-called circuit number. The circuit number is just given by this product, which can be derived immediately by an input circuit polynomial, because you just have to take here in the numerators the coefficients of the vertices, which can be read off by the circuit polynomial. And here in the denominator and in the exponents are the barycentric coordinates of this interior point, which can be derived by solving a system of linear equations. And with this number, I can check whether a circuit polynomial is non-negative or not. Namely, it clearly depends on this bad term, right? And this coefficient of this bad term, this f beta, the absolute value has to be bounded by this circuit number, or f is the sum of monomial squares. Then I also know that it is non-negative, and this sum of monomial squares just means my f beta is also strictly positive and my beta is also even. And then we already discussed that this is then this polynomial then is clearly and obviously non-negative. All right, to make things a little bit more concrete, here an example how to use it. So let's consider the Motzkin polynomial and assume we would know that this is non-negative. But we know it is a circuit polynomial, right? We just convinced ourselves it is a circuit polynomial, so we can use this fact here to check whether it is non-negative or not. So we have to firstly compute the barycentric coordinates. So we have to write this interior point 2, 2 as a convex combination of the vertices. And we find that the barycentric coordinates here are all 1 on 3. So now I have every ingredient to compute my circuit number. So the coefficients regarding the vertices are all 1. The barycentric coordinates are 1 on 3. So we can compute that the circuit number in this case is 3. And now we have to see if this coefficient in front of this interior point is really bounded by the circuit number. So let's see, it's -3. And the absolute value is then 3. And clearly we have that this is bounded by the circuit number. So we can conclude that f is non-negative. So this is here really an if and only if condition. The nice thing or the advantage here is that I also can check non-negativity of families of polynomials. So for instance, if you think about a generalization of the Motzkin polynomial, where we have not here a real, where we have not a specific number, where we only have maybe a parameter plus delta or something like this, I can check it in the same way, because the calculation of the circuit number does not need the coefficient in front of the bad term, right? Then I can somehow find a condition for this coefficient that this polynomial is non-negative. All right. As James already said. I don't know if it was Monday or Tuesday. So this approach can also be motivated as a consequence of the classical inequality of arithmetic and geometric means. So he showed you that that the non-negativity of, for instance, the Motzkin polynomial can be shown rather easily via the AMGM inequality. And this can be seen as somehow a generalization of this approach. So now we have the building blocks. We know that checking if there are non-negative is very easy. And if we now think about non-negative circuit polynomials, clearly they are non-negative, but to make them a larger class, we just now take sums of these guys. So we are considering sums of non-negative circuit polynomial, which gives us a certificate of non-negativity. So as for sums of squares, we also now take sums of non-negative circuit polynomials, and we abbreviate these polynomials via song. Right? So let's formally define this set. We give it the description Cn to d. So the set Cn to d contains every polynomial in our real finite vector space Rn sub d that can be written as a decomposition of non-negative circuit polynomials. Okay, so far so good. But now we really want to see if this set forms a cone and somehow how this lies regarding the SOS cone. So firstly, one can rather easily show, yes, indeed, it is a convex cone, clearly living inside the cone of non-negative polynomials. And if we compare this song cone with the SOS cone, we really see that these two cones intersect a bit, but they not contain each other. So to be more specific, the song cone only lies in the SOS cone in these three cases. So in the univariate case, in the quadratic case, and in this specific case for binary quartics. And maybe this, because now it's Friday, right, rings a bell for you. You should have seen this a little bit on Monday. Namely, these are exactly the Hilbert cases where the SOS cone coincides with a cone of non-negative polynomials. So clearly, in these cases, the song cone will also be contained in the SOS cone. But in all other cases, this is not the case. So to say we find song polynomials that are not sums of squares. Think about the Motzkin polynomial. This is an instance of a polynomial that is song, but not SOS. And also the other containment doesn't hold in general, right? So also the SOS cone is not contained in the song cone. So we really here found a cone that is independent of the SOS cone. And as a last ingredient to really call it a non-negativity certificate was that it better be satisfied for many polynomials. And that is somehow given by this result that the song cone is full dimensional in the non-negativity cone, which just shows us that indeed, if the dimensions are equal, this property to be song is satisfied for a reasonably amount of polynomials. So we can extend now our picture. So the pictures you should always now keep in mind. So clearly still we have the non-negativity cone, the SOS cone lies inside, and now a new cone enters here the view, namely the cone of song polynomials here in green, which intersects the SOS cone, but they do not contain each other, so it could be painted somewhat like so. So for instance here, there lives a polynomial, the Motzkin polynomial, which doesn't live here, right? And finally, so maybe to draw a bridge to Georgina's talk yesterday, So she talked about these scaled diagonal dominant polynomials, which are also sums of squares, right? They in fact live in the intersection. So every scaled diagonally dominant polynomial is in fact a circuit polynomial. So these polynomials would lie in the intersection. But there are also polynomials which lie in neither of these cones. And on Monday, you heard about this Robinson polynomial as an example of a polynomial that is non-negative but not SOS. And for instance, this polynomial lies here. Yeah, so this also is not a Sonk polynomial. So there are polynomials that are not captured by the Sonk and the SOS cone, but which are non-negative. All right, so far to the new cone that entered our picture now, the new non-negativity certificate. And let me now come to this second part where I tell you a little bit about the geometry of the Sonk cone. So first of all, I would like to mention two more structural properties of the Sonk cone, namely the Sonk cone is neither closed under multiplication nor under affine transformations of variables. And to convince you a little bit, or to give you an idea how to see that is, so for instance, for the multiplication case, here we really mean that we can find two polynomials in Cn2d with whose product is not in N4d, because clearly the degree bumps up, right, if you multiply. And you can see this, for instance, in the case n equals 2 and d equals 1. In this case, when you take the polynomials to be 1 minus x1 and 1 minus x2 squared, their support is given here. We can show that these polynomials are non-negative circuits. And if we multiply them, this is this polynomial here, and the support is given by this whole square and interior point, that this product is in fact non-negative, but not a Sonk polynomial anymore. You can show that by contradiction if you assume there would exist a Sonk decomposition and then show, okay, you don't have somehow enough weight on these vertices to really make it Sonk. So we really have here a product of two circuits that is not Sonk anymore, which is a witness for this result. And then the same idea can be somehow used to see the affine transformation of variables. Namely, if you think about this polynomial x1 squared, x2 squared, which is again clearly Sonk because it's just a monomial square. And then you apply the affine transformation given here to this polynomial, then exactly you end up with this polynomial, which was shown to be not a Sonk polynomial. So I would say these properties are clearly satisfied for the SOS cone, not satisfied for the Sonk cone. And from an optimization perspective, this implies that somehow problem formulations obtained by applying, for instance, affine transformation of variables can lead to very different tractability when using Sonk methods. But this has advantages and disadvantages. Yeah, clearly a choice of representation has to be done very carefully with this approach, which can make the process of algorithm design, for instance, more demanding. But on the other hand, even a small change of representation might allow to find a Sonk certificate or maybe simplify an existing one. Right? If you think about it for the SOS case, for instance, the Motzkin polynomial, every affine transformation of variables done to the Motzkin polynomial never will yield a SOS representation. You can do whatever you want to this polynomial, right? So there are advantages and disadvantages to this result. And secondly, I would like to mention the best feature, I would say, of this song cone, namely the song decomposition are sparsity preserving. And what do I mean by that? So I mean by that, if a polynomial is song, then there exists also a decomposition in which the support of every non-negativist circuit polynomial is already contained in the support of F, and there are no term cancellations between the circuits. So for instance, if you think about sums of squares, usually term cancellations can occur, and you all sometimes also need more support points than your original input polynomial to write it as a SOS decomposition. But this is not the case for song. So to make it maybe more clear, consider this polynomial here. I again plotted the support. So the red points are again the vertices, the blue points are the interior points, which correspond to the bad terms, and which then have to be somehow written as interior points of circuits when we write it as a song decomposition, right? And then you can note that beta 1, so this 0, 3 point, this lies in the simplex given by the vertices A1 and A3. Oh, this is a typo, pardon. So A1 and A3. And beta 2 is contained in two simplices, namely in this one, A1, A2, A4, and also in this one. So A1, A2, and A3. And this result states that if this polynomial given here would be song, then it is a sum of non-negative circuit polynomials which is supported only on these points. We can maybe even use less support points, but we don't have to add maybe, let's say, this point here or this point, or maybe the interior point 2, 2 here. So we don't need any additional support point to express this polynomial as a song. And again, this is very desirable because clearly this somehow reduces the complexity if we search for such song decompositions, if we know we can restrict this search to this small amount of support points. Then there is more, clearly, what has been done by now. But in fact, I also want to highlight that. So this research about song polynomials and the song cone is very much in its adolescence. So it is not as mature as the SOS research yet. So we try to work on it, but clearly somehow if you compare these two research, they are really done in different times. So this is a concept that came up in 2014, 2015, really, and SOS is really more and a well understood, I wouldn't say done with to be understood, right? But it's much more understood than the song cone. So here are some results that are already known about this song cone, about the geometry of the song cone, but again, it's still in progress. Okay, so I did not want or do not want to dwell on this further. I rather want to address this problem of checking membership in this cone. All right, so now we have understood the cone a little bit. The thing we now want to somehow address is, if I give you a polynomial, how can I check whether this polynomial is song or not? This brings us back to polynomial optimization and will eventually lead to applying songs for these kind of problems. And I want to start First, in the unconstrained case, so we don't have any constraining polynomials. We just want to minimize f globally over the whole real space. So we want to find the largest real number gamma such that f minus gamma is globally non-negative. Then the last few days, you saw how we can do so via a non-negativity certificate. For instance, with the sums of squares non-negative certificate, you did the following. So here our polynomial optimization problem involves this hard non-negativity condition. Then you say, okay, now we have a sufficient conditions for this non-negativity. I can relax this hard condition to, for instance, an SOS condition. So I asked now whether f minus gamma is the sums of squares globally, and I call this number f SOS, and this clearly gives me a lower bound for my original optimal value f star, and I even can compute this bound easily via semi-definite programming. So now we want to do the same, but instead of relaxing this non-negativity certificate to an SOS certificate, we would like to use SONC instead. And it turns out, clearly we can define such a lower bound f SONC, but it turns out that the right optimization problem to use here to really compute this bound for a large class of polynomials is what we call geometric programming. I don't want to go into depth because we generalize this shortly. So just let me mention, so geometric programs are convex. And best of all, they are known to solve very large problems. So they are very efficiently large scale solvers. So for instance, GPs can solve sparse problems with over 10,000 variables and 1 million constraints in, I would say, a minute on a desktop PC. So this is very desirable, especially if we think about what the issue with the semi-definite programming was or is. So we now have this correspondence, I would say, for optimization purposes, SOS SDP, so sums of squares, semi-definite programming, and sums of non-negative circuit polynomials, geometric programs in the unconstrained case. But what about if constraints enter the picture? So if we really want to optimize over a specific set, then the first approach via the SONC polynomial was to say, okay, maybe we can use geometric programming again. And this works for specific cases of K. And in fact, it also works for arbitrary K, but it does not yield so nice bounds, I would say. And specifically, it also only yields one bound for our optimal value. If you think about SOS SDP approach, and the key strength here was that you had this hierarchy of lower bounds. I think once it was mentioned that we call this Lasserre's relaxation. So by that I mean we have a parameter fs SOSD depending on the degree, and if I turn up the degree, then somehow this lower bound steadily converges towards my optimal value. So to say I can approximate the optimal value as close as I wish. And the theory behind this converging hierarchy was a specific Positivstellensatz. Usually one uses Putina's Positivstellensatz, which expresses a polynomial linearly in the constraints. You saw that on Tuesday. So somehow now the idea is to also find such a Positivstellensatz which can be turned into a hierarchy also for this song cone. And maybe the first naive idea is, okay, let's take a look at Putina's Positivstellensatz, take a look at the proof and see if we just can translate this into the song setting. So first question, can we do so? Answer, unfortunately not. And the main obstacle here is, I would say, the structural property I told you about, namely that the song cone is not closed under multiplication, which is a key ingredient to show this representation like Putina. But not all hope is lost, because good news, there exists just another Positivstellensatz for song, which is more Schmidtgen-like. And I don't know if you remember this Schmidtgen Positivstellensatz. So this was a Positivstellensatz in the sense that if this constraining set is compact, then I can certify positivity of a polynomial on this set without multipliers, but with products of constraints. So Putina on top was then without products of constraints, but Schmidtgen has to take the products of constraints. To see this, here is the Positivstellensatz in a very rough version. So you have a polynomial, a compact constraint set. And then if you know that this polynomial is positive, strictly positive for all x and k, then you have a specific algebraic representation given like so, namely as a finite sum of products of song polynomials and products of the constraints. So this holds in the same way also for sums of squares, right? So where we have here instead of song polynomial sums of squares, and this was the Schmidtgen Positivstellensatz. This also holds for song. Okay, so we have now a Positivstellensatz, so to say the theoretical engine behind the hierarchy. So first of all, we can now also define a parameter. Let's define a parameter f song d as the largest real number gamma, such that f minus gamma has this representation as given in the Positivstellensatz. And clearly that I can compute this number, I have to bound the degree of all involved polynomials. And let's say this is d, so this is why this parameter d here enters. This clearly gives us a lower bound, again, on the optimal value, because this representation here is a certificate of non-negativity involving song polynomials. And eventually you can really show that this parameter also yields a converging hierarchy of lower bounds in the sense that it really converges towards my optimal value. And this is degree dependent. All right, so now we have what the key feature was with the SOS SDP approach. How about the computation? So how do we compute these parameters f song d? Can we do so with geometric programming? And the answer is yes and no. So in special cases, we can use geometric programs here, but in general, we have to be a little bit more general than geometric programs, namely, we have to use relative entropy programming. And I'm not sure if you're familiar with these kind of problems. So here is how a relative entropy program looks like. So we are minimizing linear functionals subject to some linear constraints and a specific conic constraint, namely this relative entropy constraint here, which is nicely and jointly convex in the variables defining this cone. So James on Monday gave you this bigger picture of conic optimization. So you can also interpret relative entropy programming clearly as a conic optimization problem, where we optimize over the relative entropy cone. And this is just a cone which is really defined by this relative entropy function, which is given as the sum of these function here. Some also call it the Kullback-Leibler number, or some. So these are relative entropy programs. And the nice thing is, again, they are convex and efficiently solvable with interior point methods, because we have a computational tractable barrier function for this relative entropy function. And these geometric programs really comprise a subclass of relative entropy programs. So in specific cases, relative entropy programs boil down to geometric programs. There are other cases and other approaches for SONC optimization, in fact. So the SONC cone also admits a second order representation. So we can also use second order cone programming for solving SOS or SONC optimization. And in fact, we can even use linear programming when we optimize over the dual SONC cone. But clearly we have a price to pay, so usually the bounds are not as good that we get in this case. And there are also hybrid numerical symbolic schemes, etc. But given the time, I don't want to go into more detail here. Let me rather come to the last part of the talk, namely, so we extend now the picture to zygnomial optimization. So far we talked about polynomial optimization, which is basically minimizing a polynomial subject to polynomial constraints. And probably it's fairly natural to say, okay, probably then zygnomial optimization is minimizing a zygnomial subject to zygnomial constraints, whatever zygnomials are. And in fact, this is the case. So let's see what is a zygnomial. So a zygnomial is a weighted linear combination of exponentials of linear forms. So they look somehow like so. And the thing is that the exponents are real. So we have, for instance, this here is an example of a zygnomial. And then zygnomial programming, as said, is really minimizing the zygnomial subject to zygnomial inequality constraints. And we then again consider this optimal value fk star. Basically, all things staying the same. It's still a non-convex optimization problem, computationally intractable. As polynomial optimization, we can model a larger class of applications with zygnomial programs. So specifically, it is very popular nowadays in aircraft design, because we really need this allowance of real exponents in these cases, and also for chemical engineering, as we will see shortly. And somehow I would like also to give you a more natural idea of how to think of zygnomials. Namely, so how I usually see it, I see it as a generalization of polynomials. So especially for modeling reasons, we can write a zygnomial in this geometric form here, where we have the correspondence that the variables ti are these exponentials of xi. But clearly we have to reduce then the variables to the positive orthant, right? But then you somehow already see the connection between this and polynomials. So this very much already looks like a polynomial. But keep in mind, we are on the positive orthant, so the variables ti are positive. But we gain something, namely the exponents are allowed to be real. Yes, so here maybe just a very short side note. So usually the complexity of polynomials clearly is measured in terms of the degree. But for zygnomials, as they don't have a notion of degree, we measure the complexity in by the number of appearing terms. So this form here is of a zygnomial is mostly really as a thought process to be understood. So it makes more sense for computations to use the exponential form. And this is basically for various reasons, but for nothing else, you can say that just the inability to even perform changes of coordinate systems with these geometric form zygnomials make them not very attractive to work with. So usually when we work with these zygnomials, we stay in the exponential form. Alrighty, so how to now really extend this song idea in this zygnomial setting. And I should say, so historically, songs in this setting are known as SAGE, so sums of AMGM exponentials, because here, as it's sometimes the case in math or in any science and research, some approaches were developed somehow simultaneously, and this also happened here. So two approaches were developed, namely one in the polynomial case, which is the song case, and one really coming from engineers more in the zygnomial setting, and they called this approach SAGE. And this sum of AMGM exponentials, I don't want to really give you a definition, but you can think of it again, a non-negativity certificate, which certifies non-negativity of zygnomials. And as you can already guess by the name, the idea of showing this non-negativity again boils down to the AMGM inequality. That's why it's called AMGM exponentials. Again, we're taking sums of these guys. We call them SAGE. And in fact, later we saw that these two cones coincide in the right language. So if you think about the song cone and then translate it via the exponential function into the zygnomial setting, then these two cones coincide in the zygnomial setting, and you can also somehow translate SAGE into the polynomial world, and then they also coincide. So these cones in the right language, they coincide, so they have the same extreme rays. So we can use results, so to say, from either of these approaches and can translate them into the other approach. So this is very nice and fascinating that this somehow happened coincidentally, this approach, also basically to the very same time. So let me maybe just mention for the zygnomial setting, we recently developed the most general zygnomial positive Sternsatz to date. So in the zygnomial setting, we have a positive Sternsatz that involves no product of constraint functions. I just showed you the song positive Sternsatz, which in fact still involves products. So we have here in this setting a positive Sternsatz without products, and the same spiel as before. So we can show that it yields a canonical hierarchy of lower bounds. Again, they are computable via relative entropy programming. So this all stays the same, but the positive Sternsatz is a little bit more powerful, which yields better tractable and also better bounds for our optimal value. And in various cases, it was now shown that these bounds we now get with this approach, they are competitive with direct global solvers from the nonlinear optimization community, like Baron, Antigone, Lindo, on really hard signomial programs. And this signomial SAGE approach is also amenable to polynomials on the positive orthant. So we can compare on the polynomial problem also this approach to this SOS SDP approach. And here there are also various examples which show that this new approach is much faster than the SOS SDP methods on high degree sparse constraint polynomial optimization problems. And in fact, we clearly can solve much higher instances of problems, so with many more variables and higher degree. So clearly what we add here brings something new and valuable to the toolbox. Okay, given the time, I better come to an example now. So I shortly want to show you this approach for a chemical reactor design problem, namely as described by Blau and Wilder. So we have here somehow the sketchy picture you should have in mind, and the goal is to find the best design of this chemical reactor system. Here is the signomial program that corresponds to this example. And I just really wrote out the objective function. So there are also 5 non-convex constraints, but I spare you with that, so they are equally horrible. So I just wanted to show you that this is a not nicely looking signomial program. So it's also terribly scaled, right? So the coefficients in this objective alone span 12 orders of magnitude. So we have to do some pre-processing and scaling before we can somehow attack this problem. And yeah, so we solved this problem with our approach. Numerical solver, we used MoCaO, and we computed 2 instances. So first degree bound and the second degree bound gave this bound here in, let's say, 24 seconds. If we then run a solution recovery on this second bound, this gives a point x prime with objective value given like here. And we see that this point is feasible to nearly machine precision. So we can reasonably conclude that this is here really our true objective value. And we computed this in a very short amount of time, so 24 seconds. And we compared this with global solvers in GAMS, so Baron, Antigone, Lindo, and Skip. And we did this in 2 approaches, namely using this t as an optimization variable in x, so either geometric form or exponential form. And so you can see the outcome of the solver times and the lower bounds in this table, but I would say the overall takeaway here is that SAGE produced the same solution as these solvers, but with a relative entropy program that couldn't be solved in, I would say, half of the time as the fastest of these methods. And also only with Lindo here, we were able to certify the solution as global optimal. And but in contrast with Lindo, the performance is not independent if I use t as the optimization variable or x. So here you see if I use t as an optimization variable, the time is much higher than using it with x. And the performance of SAGE is independent, whether I use t or x as an optimization variable. And yes, Skip unfortunately returned no solution and no bound before timeout. All right, it's only an hour, so time to wrap up. So if that was a little bit too fast, so the take-home message of this last lecture is that we have now a new cone entering the picture. So additionally to the SOS and the non-negativity cone, we have the song cone, which lies in the non-negativity cone. And I hope I sparked your interest in its geometry and optimization. Geometrically, we clearly have now a new playground to see how this cone behaves, because it behaves really differently than the SOS cones, and so that's always intriguing. And clearly it also yields advantages for optimization, because now we just have a new tool to tackle CPOPs, so constraint polynomial optimization problems. And you even saw that we can extend this to solve some zygnomial problems. All right, with that, thank you for your attention.
Thank you, Mareike, for a nice talk. So any question from the audience? Andrew, you want to ask question? Or?
Putting me on the spot, are you, Thong?
Yeah.
Right, that was more calling out than attention.
So I noticed that with the previous talk we had, when it came to trying out different cones, they tried to find a heuristic way of generating larger cones through operations. I mean, if you start taking the Sonk code and you start using its non-closedness with respect to those algebraic operations and so on, and generate larger cones, I guess you lose the underlying kind of optimization technique that you're using to generate your lower bounds. Is that what the problem is? You know, you can't exploit the non-closedness to kind of do things to.
No. In fact, that is it is an interesting open problem that I also would like to exploit. Namely, I think if you close the cone, you should stay inside of the non-negativity cone.
Yeah, it looks like it, doesn't it? Yeah.
Right. So the question is, how can we efficiently search for this decomposition in the closed cone? That would be the question.
Yeah, that's right.
But it's definitely worthwhile to exploit, because clearly if we close it, we capture more of this cone, right?
Yeah, that's right. Yeah.
So in both cases, it would be interesting. So closing it regarding multiplication, and also closing it regarding affine transformation. And then the next question would also be, how do these closures relate? Do they relate? Yeah, I don't know, but yeah, very interesting and worthwhile to study.
Okay, that's my question.
So I have a question about the last example. So
Sure.
It seems that in your example on the exponent of fraction, like non-integers. But then in the definition, my impression is every powers are integers. Is it correct? Or
Oh yes. So here again, it's the you have to distinguish polynomial and zygnomials. So polynomials, clearly you only have non-negative integers as exponents. And I can also just use these polynomial approaches, SOS, for instance, or Sonk polynomial. Yeah. But now we extended it to zygnomials. And I told you somehow you can think about these zygnomials as generalized versions of polynomials where I allow real exponents. Right, so you can model much more. For instance, also this problem is a zygnomial problem, clearly because we have real exponents. So we can now take these zygnomial approaches, which is known now under the name SAGE, or you can translate Sonk into this setting. So we also now have methods to really approach this more general optimization problem.
But the theory, I mean, the original theory, is only for integers, exponents. Is that correct? Or?
No. So Sonk was originated in the polynomial setting, and then really other researchers worked more, because they are coming from the engineering world, I would say. They are very much working with these zygnomial programs. They came up with theory somehow to address these problems, and funnily, they also thought about this more from the algebraic point of view and came up with this concept of sage. And somehow, you know, we met and so, oh, okay, it's in fact the same if you do the translation and if you do it the same way. So there is theory that originated also in this setting, but you can really translate it.
Okay.
Yeah.
Okay, thank you.
Yeah, no worries.
So any other question from the audience? Well, if not, then thanks, Mareike, again. And have a good weekend, everyone.
Okay. Just say thanks to all those that have stuck it out the whole week and you know, gone to all the talks.
Yes.
I think it's been a very interesting period, and we've learned a lot of things. So thanks to Mareike and all the other speakers that have given us talks this week, and thanks for coming.
Thank you.
Right.